Okay, hello again. This video we'll be looking at some of the tools that we have to work out the ages of corals. So we've been looking at some of the proxy measurements that we can make in corals to learn about the past environment, but it's kind of just as important to know about when that environment was like that, to know as it is to know what the environment was like. Okay, so I'll just give myself a go. Yeah, so I guess the x-axis here, this time parameter, is just as important as the environmental reconstruction from a proxy. If you want to produce a graph of how the the environment has changed through time. Now, for the youngest corals, the ones that were sampled while they were still living, this is relatively straightforward. You can take a slab of your coral that you're going to sample and get measurements from. You pop it in an X-ray machine, and you can effectively get an image like this, where you can just count the layers back from the year that you sampled it, and they have these nice annual layers. If you're sometimes it's maybe a bit unsure that these are actual annual layers, so what people sometimes do is they come along and they dye the surface of the coral 1 year, they let it live for a year, then come back and sample it a year later, and then they'll see that there's maybe a layer of dye preserved when they dyed it, and then they can work out that that is in fact 1 year, and then they can extrapolate that back and say, well, each of the similar bands is a year. Because you might be able to see that there are other banding within here. You might be able to see that there is finer scale banding, which might be tidal or monthly banding, depending on how the coral responds to, I guess, environmental conditions as they change throughout the year. But we're going to be looking now at working out how old corals are if they were already dead when we sampled them. So we don't know the age of the top surface, and they may have been, I guess, dead for maybe thousands of years. So how do we work out the ages of those things? So one of the tools that you might be familiar with is radiocarbon dating. So just a quick brief introduction to how that works. So in the atmosphere, there's lots of nitrogen gas, because that's what the atmosphere is made of. And the atmosphere is exposed to cosmic radiation. So this is very, very high energy radiation that's basically coming from outside the solar system. So it's not coming from the sun. It's coming from basically exploding supernova, like many, many millions of light years away. And these very, very high energy particles, they hit the nitrogen atoms in the atmosphere, and they basically cause, they don't necessarily hit the nitrogen atoms as described in this cartoon here. They might hit other atoms in the atmosphere, and they effectively shatter them, and the atoms just get completely blown apart because the radiation is so intense. And that creates a kind of basically a little kind of shower, cloud, spray, maybe. I'm not sure the best word to describe it, but just a splatter maybe of subatomic particles. Now, some of those are neutrons. Now those neutrons kind of fly around until they hit something, and if they hit a nitrogen atom, that converts the nitrogen into a carbon. Okay, so we form carbon 14 in the atmosphere, and that carbon 14 is an unstable isotope of carbon. So it decays with a half-life of 5,730 years back into nitrogen. So if that was all that happened, then that would stay in the atmosphere, and that would be, fantastic for, I guess, the atmosphere, not really useful to us. But actually, that when that nitrogen gets converted into a carbon atom, it's very chemically reactive because it's just a carbon. So there's lots of oxygen in the atmosphere as well, so that the carbon is rapidly oxidized to CO2, and that conversion to CO2 means that we now have basically a radioactive carbon atom in a CO2 molecule, and that CO2 molecule now effectively becomes part of the carbon cycle. So if that carbon dioxide gets taken up into a tree, this root here, by photosynthesis, that radiocarbon will be incorporated into maybe the wood of the tree, and no more carbon will be added to the tree in kind of subsequent growth. So the radiocarbon will continue to decay, and we could use the decay of that radiocarbon to work out how old the tree is. Similarly, some of the CO2 might dissolve into the ocean, where it will react with the water and form bicarbonate ions and carbonate ions. It will become part of the dissolved inorganic carbon pool in the ocean, from which it can be uptaken by organisms. So coral might, I guess, put a little coral reef on here, little coral reef here. So we could take some of that and we could form calcium carbonate. Okay, and if that calcium carbonate, well, that calcium carbonate will have taken some of this radiocarbon in, and we can then use that radiocarbon as it decays as a clock to figure out the age of the coral. So that's kind of explained a little bit like this. So we start out with some amount of radiocarbon that's incorporated into the coral or the piece of wood, and that's due to the rate of which it's being produced in the atmosphere. So we basically start out with the atmospheric concentration of radiocarbon, which is a balance between its production and decay in the atmosphere, and also it's the input and export of radiocarbon from other sources, and we'll come on to that in a little bit. We start out with some amount of carbon, and over time, the amount of carbon decays away. And then if we can measure the amount of radiocarbon in a sample, we can effectively just calculate the age at which that sample formed, or which it incorporated its amount of initial radiocarbon. Now, there are some kind of little caveats to that, because I guess carbon has, well, it's we measure the amount of carbon-14 relative to the other components of isotopes of carbon in the sample, and there's also stable isotope fractionation of carbon. We need to account for that, and that's explained in these things down below here. So you'll see this terminology, this capital Greek delta 14C, and that's effectively the parts per thousand difference between the initial atmosphere and our sample of unknown age. And I guess another little caveat I've got over on the left-hand side is that the half-life is this value here, but actually it turns out that when we do a calculation of the radiocarbon age, we use a different value. We use a half-life that we actually know to be wrong. And the reason for that is that we thought this shorter half-life was the real half-life, and we started to make a bunch of radiocarbon measurements, and then at some point we realized that it was wrong, but if we started using the new half-life, we'd have to recalculate all of the radiocarbon measurements that had previously been made. So we decided as a community to stick with using the old half-life. So the radiocarbon ages we calculate from this are wrong, and that actually doesn't matter, because we'll see in a little bit that actually we don't actually use this radioactive decay equation that gives this nice smooth curve to calculate ages, and that's kind of shown in this diagram here. So if we were to calculate the radiocarbon age, that's on the y-axis here, of some samples, and compare that to the true age, so that the calendar age, so these are maybe samples that we know the absolute age from if they were maybe tree rings. So we can count back the tree rings of a tree and work out the exact age of that layer in the tree, and then we can radiocarbon date that. And this has been done for, I guess, hundreds of thousands of samples, and that's produced this dark or this thick blue curve here. And you can see that that thick blue curve does not fall on this this one-to-one line here, this line here. And part of that is due to us using the wrong half-life. But you can see that if we use the wrong half-life, this should still be just a straight line, and it's not straight; it's got these wiggles on it. And the reason for these wiggles on the I guess what we call the radiocarbon calibration curve is that although I guess the simplified, I'll just switch back to our simplified view of how this system works. If we were to use this graph here to work out the age, what we'd be assuming is that this process here is constant in time, and it's not. So that the flux of cosmic rays into the atmosphere does vary with time, as variously the Earth's magnetic field and the Sun's magnetic field change through time, and that variously protects us from these extrasolar system cosmic rays. Also, the amount of this radiocarbon in the atmosphere depends not only on the production. Okay, so we've got production and I guess decay. Okay, and that determines how much radiocarbon is in the atmosphere, the balance between these two. And if these two are constant, so the decay rate is constant, the production rate isn't constant. But if it was constant, the amount of radiocarbon in the atmosphere would be constant. But there's another kind of set of processes that are altering the amount of radiocarbon in the atmosphere, and that's the export and import of carbon between the atmosphere and the ocean, and between the atmosphere and the biosphere. Because if you just think about all of these different kind of places where we can store carbon, so we can store carbon in the atmosphere, and we can store carbon in the biosphere, and I guess we can store carbon in the ocean. Now, if you do think of these as reservoirs in terms of the percentage or the amount of carbon that is radiocarbon, there's going to be more in. So this is going to be more 14C up here in the. I'll just get that. So we've got 14C. We've got lots in the atmosphere, but the other reservoirs, the biosphere and the ocean, this will still have some 14C carbon in it, but because that's been isolated away from this production mechanism over time, this will have less in it. This will have less in it down here, so less 14C, because it's had a chance to decay away. So if we then mix these low radiocarbon sources back up into the atmosphere, if we, for instance, burn lots of trees, or we allow the ocean to degas CO2 out, that will lower the amount of radiocarbon in the atmosphere. So by altering the production rate and altering the fluxes between these different reservoirs, we can basically change what this starting point is. So if we have different starting points in different points in time, these will all be decaying. Oh, I'm going to get rid of all these things. We have different starting points in time. These will all be decaying at the same rate. Okay. But if we were to then measure a radiocarbon concentration, not knowing what the starting composition was, we would get a range of different ages, which is a problem. So that's effectively the reason for these little lumps and bumps on this radiocarbon calibration curve are the exchanges of carbon between these different reservoirs. And if we actually zoom in, we can see that over on the right hand side on these little wiggles here, we can actually see that there are some times when actually it looks like this calibration curve goes backwards. So what this means is that if we were to make a measurement of the radiocarbon age, so the radiocarbon concentration, which might have some error associated with that measurement, that can end up giving us, okay, a very wide age estimate. There are some periods in time when the opposite is true. We end up actually getting a much smaller age error from a same kind of measurement error. We might end up with a very accurate, precise measurement of the age. And in fact, there are times when we end up with multiple different age estimates from a single measurement. Okay, so just to point out that what we effectively are doing when we make a radiocarbon age measurement is we're not actually using the decay constant and the decay of radiocarbon to calculate the age. What we're doing is we're using this calibration curve. So we're using basically a database of measurements of things that we know the age of, mostly measurements of trees, which have been layer counted back kind of thousands of years, or maybe layered lake sediments, which have annual layers in which we can count, and then we can measure the leaves that have fallen into that lake and calculate the age of those. And what we effectively do is we measure the radiocarbon age using the wrong half-life, getting a number that we know is wrong, and then we use this curve and we read off the true age. And that's how we basically work out the age of things using radiocarbon. There's an additional problem, which I've kind of already alluded to, in that the source of the carbon into our sample, that's not necessarily coming directly from the atmosphere. So it might not be coming from this zero age initial amount of radiocarbon in the atmosphere. Because different parts of the carbon cycle effectively have different ages of carbon in them. And we can see that here in the top slide, or the top section. So this is a slice through, I think it's the Pacific Ocean. And you can see, so we've got Antarctica in the south, and I guess this up the top would be Alaska in the north. And if we look at the radiocarbon content, this delta 14C, so 0 is effectively the modern atmosphere. We've got the surface layer that's got relatively a lot of radiocarbon in. It's got very close to the atmospheric values of radiocarbon, but the deep ocean down here has got much less radiocarbon. So it's got a minus 200 parts per thousand of the atmospheric concentration. And if we think about what that means in terms of how long the carbon in the deep ocean here has been isolated away from the atmosphere, if we look at this part, 200 parts per thousand difference from the modern atmosphere, that would effectively look like that carbon has been isolated away from the atmosphere. It's been decaying for 2,000 years. So if we were to sample a coral that has basically or that's living in the deep sea, if we were to get rid of these annotations, if I was to go to this part of the ocean here, and there's a coral kind of down here, and I was to sample that coral with a remote kind of submarine, and it was still living, and I was to take probably the calcite from that deep sea coral, and that's got its carbon from the dissolved inorganic carbon in the water, and I was to date that, it would appear to be 2,000 years old, even though should have an age of 0. So this is called the reservoir effect, or the reservoir age of the sample. It's the initial age of the carbon that was incorporated into that, when that sample was living. And now in the modern ocean, we also have this additional problem, which is shown in the bottom. In the surface ocean has had a lot of radiocarbon added to it. Okay, so we've got much more. We've got basically positive delta 14C. So we've got more radiocarbon in the surface ocean than should be in the atmosphere. And that makes absolutely no sense. Right? That makes no sense whatsoever, because it should be decaying away since it was produced in the atmosphere, but it is in fact there's more. So where has that come from? And it's kind of a little bit alluded to in the title of this plot. It's come from bombs. So in the 60s and well, I guess the 50s and early 60s, a variety of countries decided that it would be a good idea to let off a whole load of nuclear weapons in the atmosphere. And those nuclear explosions produced a huge quantity of radiocarbon. So actually, when we refer to this how much radiocarbon is in the atmosphere, we tend to use the value in 1950 because this was before widespread nuclear testing. So that's the value that we use for kind of the starting point with our radiocarbon calibration ages. It's also when we calculate a radiocarbon age, it's the point we use as 0. So if something is 0 age in terms of radiocarbon calibration, our starting point is actually 1950. It's actually 1950 and a half. But hey ho, details. So if we were to, I guess the year now is, I guess, 2020. So in terms of the calibrated radiocarbon age of this year, it's minus 70. So it's just a thing to mention when I guess using kind of geochronology and dating systems, especially when you're looking at very young samples, it's worth considering what is 0 age. So quite often, if you're counting layers back in a coral, you might use kind of the Gregorian calendar and give the age in kind of common era or Anno Domini. But with some radiometric dates, there's a variety of different ways of defining 0. So some systems use 1950, mostly radiocarbon. Some dating methods use the year 2000, purely because it's a round number. Some use the date at which the sample was actually measured, and sometimes in the paper they might even say when that was, but that might just be an assumption that the authors have not really thought about the details too deeply. So just as I think about when the 0 actually is, and of course bear in mind that in the Gregorian calendar there is no year 0, so it goes from 1 BC to 1 AD. But that's, I guess, that doesn't matter anyway. For this, that's just a thing that maybe you should know for pub quizzes, that there is no year 0. Anyway, so is this a disaster, this extra radiocarbon in the atmosphere? So this, you would think that this would kind of completely mess up all of our ages of samples if we had samples from the 70s and we wanted to kind of radiocarbon date them. It would be a complete showstopper that we've added all of this radiocarbon to the atmosphere. We wouldn't be able to use the radioactive decay, but actually we can. So rather than actually use the radioactive decay, what we can use is we can actually look for this spike in the radiocarbon content in our samples as an age marker. And that's what's being done in this sample here. So we'll have a look at how this has been used in the past, but this is a bamboo coral, so it's got an organic kind of rich component and a inorganic calcium carbonate component. And the calcium carbonate component, that is getting its carbon from the dissolved inorganic carbon in the water. So this is living in the deep sea. So that deep sea doesn't have this radiocarbon spike in it. But the organic component, the coral is filter feeding from organic material that's being produced in the surface ocean, and then that's settling down to the water column. And you can see in that organic component, we can see this spike in radiocarbon concentration to values far above what we think the atmosphere is. So we can say that this spike in the radiocarbon, that is this spike here, and we can assign an age to the coral. Okay. Whereas the the inorganic component, that's because it's in the deep sea, it hasn't seen that spike yet. Okay. So in this case, we can, because some component of the carbon in this coral is being kind of sampled from near the atmosphere, so the surface ocean, even though the coral is living in the deep ocean, we can use that marker of that radiocarbon spike to provide some estimate of the age of the coral. Okay, so we in some cases we might not be able to use radiocarbon to calculate accurate ages of corals because of this large reservoir effect, this very large, certainly in the deep ocean of maybe thousands of years, but actually even in the surface ocean, the reservoir age of the water is approximately a couple of hundred years. So if you were to, I guess, if you were to sample fish and chips, okay, the chips have come from potatoes, they've got their carbon from the atmosphere, whereas the fish, they've got their carbon ultimately from the ocean. And the fish would be maybe up to 400 years older than the chips, which sounds disgusting, but is true. And there's a lot of uncertainty about exactly how much older the ocean is in any particular place, because it depends on air-sea gas exchange, ocean circulation, the carbon pump, all these kind of things. So it'd be nice if we could get another way of getting an age of the coral. And one of these methods that's used quite widely is uranium-thorium dating. So I guess just like in the proxies, trace element proxies video, we saw that the calcium carbonate part of the skeleton, that can incorporate some elements into it, either replacing the calcium, maybe sometimes even replacing the carbon and oxygen. And uranium is one of these elements. So we can incorporate small amounts, maybe parts per million concentration of uranium into the coral. But actually, the other elements in the radioactive decay chain following on from uranium tend to be excluded from the coral. So over time, the uranium that gets incorporated into the coral, this guy here, and I guess also this isotope here, these isotopes of uranium, they get incorporated into the coral when it forms, and they decay and produce isotopes of thorium. We can measure the ratio of uranium, and we can measure to thorium, so we can measure the amount of thorium compared to the amount of uranium. And as the coral gets older, after it's died, the amount of thorium will increase as it is produced from the radioactive decay of uranium. So we can make these measurements in the lab, and we can actually get reasonably accurate ages of corals from minus 50 years. Okay, so maybe only a few tens of years old from present. So remember, in some cases we use, I guess, we use 1950 as 0. So I guess the year 2000 would be minus 50. We can also date corals up to maybe 500,000 years old. So obviously we're not going to be able to get the same degree of precision when something is that old, because the ratios get progressively, they change progressively slower as you get older and older and older. But nonetheless, we can date a very wide range of ages, and we can date them reasonably accurately using this method. So how can we combine these two techniques together to find out something useful? So the uranium-thorium age, we could maybe date the true age of the coral, but we could also measure the radiocarbon age of the coral. And we know that these things shouldn't be the same because the radiocarbon age is affected by the reservoir age of the water. So maybe we could use these two techniques together to actually measure the radiocarbon age of the water. So this is a study that was done, quite a while ago now, by Andrew Burke, who's now based in St Andrews. And what she did is she went out to the Southern Ocean and sampled a whole bunch of deep sea corals down to almost 2,000 meters water depth. And she measured the true age using uranium-thorium, and measured the radiocarbon age using radiocarbon measurements. And what you can see here is these data, the corals are the kind of the colored symbols. This kind of wiggly line here, this is the atmospheric radiocarbon content back in time. So you can see that that's going up, and that's partially due to the half-life being incorrect, but also these exchanges of radiocarbon between the ocean atmosphere and the biosphere. And what we can see is that, first of all of these coral samples, all of the coral samples, they are below the atmospheric curve. So they have got less radiocarbon in the atmosphere. And that makes sense because the ocean's been isolated from the atmosphere for some time, allowing the radiocarbon to decay away. But what we can see here is that these different sites in the ocean, they are denoted by the different colors. They are depleted in radiocarbon by different amounts. So we can see that this, I guess the South Atlantic in lower circumpolar deep water, that seems to have the biggest offset, okay, from the atmosphere. Where if we look at this, the Chilean margin here, these blue data, the water mass here, Antarctic intermediate water, that is offset by less. So what we can say here is that the Antarctic intermediate water has got a radiocarbon age that's a lot less than lower circumpolar deep water. So different water masses in the ocean have got different radiocarbon ages. And that's expressed over on the plot on the right here. It's just basically looking at effectively the radiocarbon deficit in different water masses. So basically, you can see that the blue, the Antarctic intermediate water, is approximately 1,000 years old in terms of its radiocarbon age, whereas other water masses are older. Okay, so these round one down here, maybe almost maybe up to 4,000 years old, which is, it's been isolated from the atmosphere for what would seem like 4,000 years if you were to radiocarbon date it. And we can see, because Andrew has dated a whole bunch of corals of a whole bunch of different ages, we can see how these different ages of water masses have changed through time. So we can see that before 15,000 years ago here, the deep ocean had a lot of very old carbon. It was being isolated from the atmosphere for quite a long time, whereas after 15,000 years, the radiocarbon age of that same water mass, or those same water masses, is now much younger. So there's been a dramatic change in the carbon cycle in the ocean across this period of time. And that has impacts for how much radiocarbon, or how much carbon, in fact, is in the atmosphere. And we'll maybe discuss this in the old tutorial. Another way that we can use this tool, and we've seen this little coral before, we can make age estimates of the organic component. So that's this part of the coral here, and we can make measurements of the inorganic component here. So the organic component, phytoplankton are basically producing little particles of organic matter in the surface ocean. So they are sampling the surface ocean radiocarbon content, so near the atmosphere concentration. That organic matter sinks down through the water column where our coral might be sitting. That's a circle denoting coral, obviously. And now that coral will be getting its carbon to form the C calcium carbonate. That will be getting it from the dissolved inorganic carbon in the water. So that will go into the coral here, whereas the organic component will be getting its carbon from, this will be the C organic, getting its carbon from there. So we can look at the age difference between these things. So that's what we measured in this kind of this white circle here, and the I guess the tissue sample that's here, and we can see that the radiocarbon age of the inorganic component of the calcium carbonate, that is the same as the radiocarbon age of the water that coral is living in. That's kind of here. whereas the radiocarbon age of the organic component, that's the same as the surface concentration there. So we can actually use a single coral now to effectively measure the radiocarbon age difference between the shallow ocean and the deep ocean. So that's also telling us something about the isolation of the deep water masses, how different they are from the surface. Okay. So why would we care about that? So maybe this is something that we can discuss in the tutorial. What is it about deep water mass ages that's of interest to, I guess, the environmental scientists? So what do we actually mean by the age of the deep water? So think about what that actually means, and think about what about the water mass changes with age. So obviously, as the water mass sits down in the deep ocean, it's going to be losing radiocarbon as it's decaying away, and it's not being added because it's only being produced in the atmosphere. But what else about that water mass will change? Okay, think about what will change in terms of its maybe temperature. Will that change? Spoiler alert, it will not. But what about the other things? What about the pH of that water? What about the carbon content of that water? The regular carbon, not the radiocarbon content of that water. What about the oxygen content of that water? What about the nutrient content of that water? How will those things change through time? Okay, so these are understanding the changes in those parameters. That's why we want to know the radiocarbon age of the water. Why we want to know effectively the age of the water. Okay, so I think we'll leave it there for this kind of thing. That's been another long one. Oh dear. But maybe some things to discuss for our tutorial fun times.